Welcome to the afternoon session. Our speaker is Ritwik Mukherjee of NICER. He'll speak about counting planar degree D curves in P3.
So first of all, I would like to thank the organizers for giving me a chance to speak at this discussion meeting. So the title of my talk is Counting Certain Things. Okay, so first let me explain the meaning of this word counting. So this is basically, my talk will be on enumerative geometry. So let me just briefly explain what is this. What is the question you ask in this subject? The nature of the question is as follows. How many geometric objects are there that satisfy some constraints? So the simplest example of an enumerative geometry question is how many lines are there through 2 points. So my geometric objects here are lines and passing through a point is a constraint. So the basic idea is that you study the space of geometric objects. The hope is that this is a nice compact manifold or at least something on which you can do intersection theory, and this constant you have to interpret this as some cycle, and this number which you are getting, this how many is the intersection number of these cycles on this variety. This is the basic hope. Okay. So more interesting question is you are given 4 lines in 3-dimensional space, 4 generic lines. How many lines intersect all the 4 lines? This is a more interesting question. You can think about it. The answer to that is 2. So the crucial thing is you have to impose exactly the correct number of constraints so that you at least expect a 0-dimensional space, and then hopefully it is compact, and then you can ask how many are there. That's the basic strategy. Right. So with this introduction out of the way, now let me say what are the 2 basic types of questions people study in enumerative geometry. I'll focus on enumerative geometry of curves in projective space. So the first type of question is as follows. We look at my geometric objects are degree D curves in CP2. So right now, ignore this CP3 for the moment. For a large part of the, at least for half an hour, we'll only be talking about CP2. Ignore this CP3 for now. So we'll look at degree D curves in CP2, and what is my meaning of the word curve? This is the crucial object here. So the meaning of curve in question 1A is, it is the 0 set of a homogeneous degree D polynomial. This is what I mean by a curve. So in particular, it is the 0 set of a section of this line bundle. So you look at a holomorphic section of this line bundle and you look at its 0 set, and that is basically your space of curves. That's a very understandable space. It's a projective space of a big dimension. Okay, so this is all non-zero holomorphic sections up to scaling. Right? This is my definition of a curve. And so one question which, very important question in this area is the following. So let us write it like this. So this number is the number of degree D curves in CP2 that pass through. So what are the type of constraints I can place? The constraints can be that it passes through certain set of generic points. So it passes through a certain set of generic points. The other type of constraints I can put, the other type of constraints is that it has some prescribed singularities. So for this entire talk, we'll only be talking about honest nodal singularities, and that has delta nodal singularities. So nodal singularity means that the curve locally looks like this. After a local change of coordinates, your curve looks like this. Okay, this is the meaning of a nodal singularity. So x square minus y cube equal to 0 is not a nodal singularity. Okay. So I'll ask you to take this on faith. Asking the curve to have a node somewhere, having a nodal singularity is a codimension 1 condition. So delta nodal singularity means it has diminished your dimension of space of curves by d dimensions, and the remaining degree of freedom, I'll say that it has to pass through so many points. So the basic question is, what is the dimension of the space of degree d curves? And it's a simple dimension counting argument. You can just find out the dimension of this projective space. So the dimension of space of degree d curves, it's a projective space of dimension d times d plus 3 over 2. So what is the correct number to put here? The correct number should be d times d plus 3 over 2 minus delta. This is the correct number. So this kills off so much dimension, and the remaining delta degrees of freedom are killed by asking it to have so many nodes. This you at least expect to be a finite number. Okay, indeed this is a finite number. So what is known about this number? What is known about this question? I'll say shortly. Okay, right now I've just defined this number. Okay, this is one question you could ask. And of course you could ask similar questions with higher singularities. As far as this talk is concerned, we won't go into that. Not really. So I asked it to have a node somewhere. Asking it to have a node at some specific point imposes 3 conditions. So asking that node, the point itself is a variable thing. There is 2 degrees of freedom for that, and so it is plus 2 minus 3. Okay. So this is first type of question. This is The second type of question is as follows. Second type of question, 1B, not 1A, 1B. My definition, so I'm looking at degree D curves in P2, but my definition of a curve means the following. And this is the setup in the study of Gromov-Witten theory, which is that you fix a Riemann surface, fix a genus G surface, and you look at maps. So look at maps. Not zero sets of polynomials, not any line bundle. You look at maps, and of course by maps I mean holomorphic maps. Definitely you look at holomorphic maps, and you ask these maps to represent a specific homology class. Okay, this is called a degree D map. Okay, and you ask how many such curves are there passing through the right number of points. So let us, for this entire talk, fix G to be equal to 0. Okay. For this whole talk. We'll not get into what happens when G is bigger than 0, except maybe at the end of the talk. And so the question is, you look at maps, so when G is equal to 0, this is CP1. Okay. So you look at degree T maps from CP1 to CP2, and also you can equally see, you can easily see that you can generalize this. You can, instead of CP2, you can put some other manifold here, reasonable manifold, and you can look at holomorphic maps which represent a specific homology class. That is the setup of studying Gromov-Witten invariants. Okay. So you look at holomorphic maps of degree D and ask how many. So I'll make that precise in a moment. So the precise question is as follows. Okay, so although I'm saying fix G equal to 0, I'll probably emphasize G is 0 a few times. So the notation for this number is, I'll write little n here to distinguish it from that capital N. So I'll probably put CP2 here, and I'll also probably say G is equal to 0. Okay, if I forgot to write G equal to 0, that's understood, but let me emphasize this. And this is just the number, no constraints, number of genus 0 degree D curves in CP2. Of course, there are infinitely many of them, and now I have to impose certain constraints. So I have to make them pass through the correct number of points. So to figure out the correct number of points, I have to figure out what is the dimension of the space of these curves. So if I have time, I'll maybe give you a heuristic reason what is the dimension of the space of curves. Right now, let's accept this fact. The dimension of space of genus 0 degree D curves is 3D minus 1. Let's accept this fact. And at least for D equal to 1, you see what I'm saying is correct. So I'm saying that the space of lines is 2-dimensional. That is probably something you can believe. And also for D equal to 2, you can see this is a believable statement. I'm saying that the space of conics is 5-dimensional. That is, again, something you can probably believe. So that passes through 3D minus 1 points. This is the precise question. Okay. And these two questions which I've written on the board, 1A and 1B, are different questions. A completely different setup. My geometric objects are completely different. And more importantly, the space of geometric objects. Here, the space of geometric objects is much more difficult to understand. Here, the space of geometric objects is a much more tractable space. It's a projective space. And so the question is, what is known about these two questions? Any questions? So I'll start with question 1B. So this is in 94, I think. So this is the famous work of Kontsevich, Manin, and also independently Rowan and Tian. So there is a explicit formula for these numbers. So if I have time, so right now I'll not say anything about how they get the formula. So hopefully towards the end of the talk, maybe last 10 minutes, I will give an indication of how to get this, how to get the formula. So this is the one which is actually more relevant for our talk. But before I get into the details of this, I want to now talk about the other side of the question, which is you look at the zero set of polynomials and ask them to have nodal singularities. How many such curves are there? And what is the status of that question? So that question is very well understood. This pretty much whatever you want to know about this question is actually known. So I'll just give a very short overview of this question. And then the main purpose of today's talk is I want to see how these two numbers are related to each other. These are two different numbers. They are not the same numbers, but how can you use one to relate the other one? This is what I would like to talk about. Okay. Right. So status of question 1A is there is a explicit formula for all D and delta. Okay, so many people have contributed towards this. So I'll just mention the one name which is relevant for us. Okay, so this is, so even before this, this is done by Martin Kuhl, Vivek Shinde, and Thomas. So of all the things I'm mentioning this because this is the one which is relevant for today's talk. The others, many other people have also worked out, contributed towards this, which I'm not mentioning right now. Okay. Right. So now the question I want to address is, how are 1A and 1B? This is the main question. So in a nutshell, what I mean is that suppose somebody makes a claim for a formula for counting rational genus zero curves in CP2, it produces numbers, and somebody claims a formula for counting delta node curves in CP2 for any delta. Is there a way to cross check? Is there a consistency check one can do? They're not the same numbers, but is there any relation between these two numbers? So let us look at this. Let us probe this number a little bit more carefully. So let us look at. So let us see for d equal to 1, what am I saying? For d equal to 1, I'm saying how many lines are there through. So what was the number? 3d minus 1. So 3d minus 1 is 2. So how many lines are there through 2 points? And clearly the answer better be 1. Okay. So of course it is 1. Okay. Next. What am I saying for d equal to 2? For d equal to 2, I'm sort of asking this a similar question, which is that how many conics are there through. So what is 3d minus 1? 3d minus 1 is 5. How many conics are there through 5 points? And again, you can see even in that question, if you look at the space of conics, the space of conics, if you think of conics as the zero set of a degree 2 equation, you see it is a P5. Okay, and passing through each point imposes a hyperplane, and so it's going to be intersection of 5 hyperplanes in P5, and so the answer better be 1. And so again, the answer is 1. Okay, there's nothing interesting in these two questions. These two questions are simple linear algebra. There's nothing more to it. The first interesting question starts from d equal to 3. What am I asking for d equal to 3? For d equal to 3, let's look at the dimension of the space of cubics. So now it's tempting to say, let's look at the dimension of the space of cubics. Space of cubics you'll see is 9-dimensional. This is a P9. And so if you're naive, you would say this is the number of cubics passing through 9 points. But you can plug this in d equal to 3 here and see it is 8. So why is this 8 here, and why is the dimension of that space 9? What is going on here? And so the point to notice that this is g is equal to 0. This is the crucial point. So let me remind you now of the following fact. So suppose you have a smooth degree d curve in P2. Its genus is d minus 1 times d minus 2 over 2. So in particular, for d equal to 1 or for d equal to 2, the genus is equal to 0. Okay, but what is the genus of a smooth degree 3 curve? The genus of a smooth degree 3 curve is 1. Okay, but what am I asking here? I'm asking here to count genus 0 cubics that pass through certain number of points. Is it possible for this to be a smooth cubic, or rather its image to be smooth? It is not possible. And so the only way a cubic can be a genus 0 cubic is if it has a node. Okay. So the correct interpretation of this question is that this is the number of cubics through 8 points that having one node. That's the only way you can have a genus 0 cubic. And so this ought to be, if everything has been done correctly, the answer to this question ought to be the same as the answer to capital N, d equal to 3 and delta equal to 1. These two numbers ought to be the same. Anything more than that, I'm not claiming. Okay. This equality on its own doesn't help us to compute either this number or the other number. You have to find a way to calculate these two numbers, but if two people come and claim that they have computed these two numbers, this is one way to check if they're consistent. And indeed, of course, they are consistent. This number is quite famous. This is 12. Okay. But I'll now proceed further and see what happens when d is equal to 4. It's not as simple as you might think. I think I'll erase this part. Questions? Yeah. Yeah, they did. Very much so. Yeah, sure. Yeah. They developed it, in fact. No, I mean, these numbers are Brahma-Whitman invariants. Maybe they didn't use that modern language, but no, I mean, they basically developed the language through this question. Yeah. The number of cubics. So by cubic, I mean the zero set of a degree 3 polynomial. Most of them are going to be smooth, and in fact, most of them are going to be genus 1. Okay, that is 9-dimensional. So if I just ask how many cubics are there, I have to make them pass through 9 points. But this is not saying cubics. This is asking for genus 0 cubics, not cubics. This is the number of genus 0 cubics. And so the only way you can, for a cubic to have genus 0 is, so for d equal to 3, this number is saying how many genus 0 cubics are there that pass through 8 points. If you ignore that word genus 0, you have to replace that by saying cubic that has a node. Yeah. Yeah, sure, exactly. Why it is 12, I didn't justify. That's a different matter. Yeah, so just to repeat, this equality doesn't help me further to get what this number is. Some way or the other, I have to find this number answer, but this is a way to cross-check that these two computations are probably correct. So I'll just proceed one step further till d equal to 4, and then I will start talking about other things. So what happens with d equal to 4? So d equal to 4, how many points is it passing through? This is passing through 12 minus 1, which is 11 points. And so what is the dimension of the space of quartics? The space of quartics is 14 dimensional, as you can see. Okay. So there is a discrepancy of 3. And indeed, now you can see that there should be a discrepancy of 3. What is the genus of a smooth quartic is 4 minus 1 times 4 minus 2 over 2, which is 3. So genus of smooth quartic is 3. Okay. And so if you were being naive, you would think that what is the relationship between these two questions? You would say that, well, the number that I calculate in this question, this perhaps should be equal to the number of curves in CP2, number of degree 4 curves in CP2 with 3 nodes. You might think this. This is what you might think. So a smooth quartic has genus 3. The only way you can get after making it pass through the right number of points, the only way you can get a genus 0 quartic is if it has 3 distinct nodes. Okay, this is what you might think. And the answer to this question is, this is 620. And the answer to this question is, this is not 620. This is 675. This is 620 plus So why are these two numbers not the same? The answer is very simple. I said here, I want to count the number of degree D curves. Nowhere did I say that this has to be irreducible. This is not necessarily irreducible. Nowhere did I say they have to be irreducible. Okay. So I'm counting vertex through 11 points that have 3 nodes. And so most of them are going to be genus 0 quartics. Okay. But what about these remaining 55 quartics? It's very simple. So you have a quartic through, so this is going through how many? 11 points. 3D minus 1 is 11. Okay. So you can have a cubic, you can place a cubic through 9 points and a line through 2 points. Okay. Cubic and a line, they intersect in 3 distinct points, and that is basically a quartic with 3 nodes. Okay, and how many ways are there of doing that? So out of these 11 points, you choose 9 of them, and through 9 points, you can place 1 cubic, and through 2 points, you can place 1 line. And that is indeed here. And so this is indeed correct. Okay. So the point of all this is that these two numbers are related to each other. They are not the same. Okay. You are never going to get this number is equal to another version, equal to that other number. With some effort, you can check that these two numbers are consistent with each other. Right. Or basically, you have to subtract off, figure out somehow what are all the reducible pieces, subtract that off, and then you'll get this number. And this calculation, this 55, may or may not be so easy. Okay. In these cases, it is. The particular question I'm going to talk about, it is not that easy. Yeah, so I was cheating not smooth quartic. To have genus 0, yeah, having 3 nodes is not the only possibility, but whatever other configuration you are going to think about, it is not going to pass through 11 points. So for example, it could have a triple point, but triple point is, for it, if a quartic has a triple point, it's not going to be able to pass through 11 generic points. Okay, any other configuration you might be thinking about, 11 points is too much for that. Yeah, sure, that requires you have to think a little bit for that. But it could be 2 nodes and 1 cusp also. That is also genus 0, but again, it's not going to pass through 11 points. Or 1 node and 1 tack node. Yeah, after it passes through the right number of points, yes. Yes, yeah, yes. After it passes through the correct number of points, yes. Yeah. In this case of counting rational curves in CP2, yes, that is true. Yes. Okay. So this is the basic background. Now I'll start saying something new. Let me erase this. So this is roughly in 2005, these two people, Kleiman and Fine, they consider the following question. Consider a family version of question 1a. So this is roughly in 2005. So this is considered in the paper node polynomial for families. So what does this mean? So you can now easily see that instead of looking at degree D curves inside CP2, this could be generalized a little bit more by saying let X be a algebraic surface and let L be a sufficiently ample line bundle, and look at holomorphic sections of this line bundle, that is your space of curves, and you ask an enumerative geometry question about the set of, space of holomorphic sections, okay, which represents some specific homology class. Sorry, about the space of holomorphic sections, let's say which have delta nodes. Okay. So you take your X to be CP2 and your L to be O of D. Okay. So the family version of this is, suppose you have a varying family of these X. Okay. So as T varies, you get a different X. Okay. They are all biholomorphic to each other, but it is fundamentally a different X. I'll give you a specific example, and on top of this, you have a line bundle. Okay. And you ask an enumerative geometry question about this family version. Okay. So I'll not make this more precise, I'll just give you a specific example. This is the example I want to focus for the remaining 23 minutes. Okay. So now remember the CP3 which was there in my title, and also remember the word planar. So the example to keep in mind is, look at planar degree D curves in CP3. So what do I mean by that? I mean the following. So this means that look at curves whose image lies completely inside some CP2 sitting inside your CP3. Okay, this CP3 is fixed, but which is this CP2? It keeps on varying. Okay, so this you can think of this as your X of T. And for each CP2, there is a O of D sitting on top of that CP2. But as that CP2 changes, that O of D also basically changes. Right. And so let me ask and the nature of the constraints are, so we are looking at curves in, so these are curves in CP3. So this is sort of an enumerative geometry question about curves in CP3, not in CP2, but the condition is that the curve has to actually lie completely inside some CP2. Most degree D curves will not lie inside a CP2, okay, unless it happens to be a conic. Okay. And so the question now is the following. So let me write it this way. So there's too much notation here, I'll explain it in a moment. Can I erase this? So this number is the following. You can probably guess what it should be. It is the number of planar degree D curves in CP3. Okay, so now, let's say having delta nodes, and now I have to finish this sentence by putting in appropriate number of constraints. Like I finish all these sentences by saying that they pass through so many points. Now we are looking at curves inside CP3. Inside CP3, what are the possible types of constraints? The possible type of constraints are they either intersect some given line or they pass through some point. Okay, these are the type of constraints. So that pass through K1 lines and K2 points. And so what is the relationship between these constraints? The relationship between these constraints is how much ever they reduce the dimension of your moduli space, the sum total of those codimensions should be the total dimension of your space of planar degree D curves. So having a node, so I'll ask you to take this on faith right now, it's not difficult to see this. Having a node, indeed, as before, it reduces the dimension by 1. We are now in CP3, so intersecting a line is actually a codimension 1 condition. Inside CP2, intersecting a line is no condition at all. Any curve would intersect a line. But inside CP3, intersecting a line is saying something. You have a curve and it intersects some line is imposing a condition on the curve. So intersecting a line is a codimension 1 condition. And passing through a point is actually a codimension 2 condition. Saying that a curve actually passes through a point is actually reducing the dimension of your space by 2, not by 1, as in CP2. So this plus 2 times K2 is whatever is the dimension of your space of degree D curves. And the dimension of your space of degree D, planar degree D curves is the following. So what is the dimension of the space of degree D curves in P2? It is D times D plus 3 over 2. So it is that dimension plus whatever is the dimension of the space of P2s inside P3. So space of P2s inside P3 is basically a Grassmannian. It is G34, which is basically isomorphic to P3. So it is 3 more than that. Okay. So even I'll ask you to accept this for now. It's basically some number. So the sum total of this has to be the right hand side. Okay. And so this is my number. I mean the question which I have defined. So now the question is what is known about this number? And so the answer is quite nice. I think I'll erase this. Theorem. This is in the paper. There is a full formula for so there is a formula for this when delta is less than or equal to 8. This is by Kleiman and Fine. And quite recently, just last year, there is a formula, there is a clean formula for all delta and all. Okay, and so this is, I'll just say a little bit about this. The proof is by suitably modifying the proof of what Kuhl, Shende and Thomas do for curves in P2 and a use of Atiyah pot. Sorry? Yeah, right. Sure. So sometimes I might just, I might omit this if it is clear. I mean, I might not always write this K1 and K2. So so this Theis-Larker, he basically modifies the proof of what Kuhl, Shende and Thomas do to get a formula for delta nodal curves in P2, and then there is a second step which is using a Atiyah bot localization to calculate an Euler class. Okay. So basically this is whatever you want to ask about delta nodal curves is basically known. Okay, so now I have just 15 minutes left. I'll now talk about an ongoing work we have been talking about, we have been pursuing related to this. So, with this background, now you can ask the following question. Is there a stable map analog for this question? So, this question being, let's call this 1C. So this whole thing, what is going on here is basically a family version of looking at curves as the zero set of some polynomial. You have a line bundle over X, you are looking at a family version of this setup. Okay. Is there a stable map version of this question? The answer is yes, of course, there is a stable map version, and the setup should be as follows. Consider the following question. You look at maps from CP1 to CP3. So in usual Gromov-Witten theory, what is the question we'll be asking? We'll look at degree D maps from CP1 to CP3, and you'll impose enough constants and ask how many are there. That is not the question I want to study here at all. The question I want to study here is, my geometric objects are, look at holomorphic degree D maps such that the image of U is inside some P2. Most holomorphic degree D maps are not, their images are not going to lie inside some P2. And this is basically essentially a family version of this question. You look at holomorphic maps from CP1 to CP2. So in Gromov-Witten theory, you look at maps from CP1 to X, you just replace this by some X of T. Okay, it's a family version of this question. Okay, and so the concrete question which you would be asking is the following. So let me put P3 here, and let me also add a planar. And again, as before, there will be they pass through certain number of lines and they pass through certain number of points. Notationally, this is less heavier. And so what is this? This is the number of planar genus 0 degree D curves passing through curves in P3 passing through K1 lines and K2 points, such that the total dimension, codimension imposed by this is same as the dimension of this space of curves. So what is the dimension of the space of curves? So passing through a line is a codimension 1 condition, and passing through a point is a codimension 2 condition. What is the dimension of the space of curves? Dimension of, so if we were looking at degree D curves into CP2, the dimension would have been 3D minus 1. So it is 3D minus 1 plus the dimension of the space of CP2s inside CP3. That is 3 dimension. So that is 3D minus 1 plus 3, which is 3D plus 2. This is the question. This is a family version of the earlier question. Right, and so I will, okay, so I have 10 minutes, I'll just give a brief indication of what we do, this is yes. No, the lines are frozen inside CP3. The lines, etc., are not completely lying inside a plane. The curve has to lie inside a plane, plus it has to intersect these K1s and all that. It's not that the line itself is sitting inside the plane. Okay? Yeah. These curves have to pass through some P2, but the P2, this line is not lying inside, completely lying inside the P2. Yeah, I should have specified that. Same in there also. Okay, so this is work in progress. This is with my student and postdoc. That. So I cannot yet say we have a clean formula, so let us say we have an algorithm. I'm hoping I can replace the word algorithm with a formula soon to calculate. We have an algorithm to calculate this, and more importantly, furthermore, so maybe I should write this as a comma. We have verified our answers are consistent with what Theis Larker obtains. So consistent meaning, I said there is a way to relate one question with the other. We have done that. We have transformed this question to the other question. It's an indirect transformation and seen that our answers are indeed consistent. So we have verified this till d is equal to 4. Beyond d equal to 4, we have not yet verified, but it's a huge calculation. So till d equal to 4, we have verified this. So I don't think I'll have too much time to say about this. Maybe I should say a little bit about how we get this formula. Yeah. Any questions? So verifying this consistency check is a much more non-trivial thing here. As I explained for that conservators thing and finding delta nodal curves for say d equal to 4, it was just a question of finding out how many reducible quartics are there with 3 nodes. That was just 11 choose 2. Here, finding out the corresponding number of irreducible things is a much more challenging question. Okay, so doing the consistency check is a more non-trivial question here.
That formula of 2017, that also gives a formula.
Not gives a formula, it is a way to, I mean, if I claim a formula for this, I can use that to verify many instances of this formula. It's not exactly, well, it's an algorithm, so that's why I have not exactly, I didn't use the word formula. So given D, K1 and K2, you'll get a number, let's say, infinite time. Let's put it this way. I'm hoping I can change this word algorithm to a formula soon, but right now let's just say it's a recursive formula. All these formulas are recursive formulas. There are recursions on D, K1 and K2.
What this should be.
Exactly, yeah, sure. Or even vice versa, I mean, this could also tell you what that should be, yeah. I mean, these are consistency checks. No, it is not obvious, but I could say naively you would expect that this number should be finite. You look at the dimension of this space of curves and it sits inside a compactification M bar, and on that M bar you intersect cycles. So you would expect it to be finite. Just like now, how many lines are there through 2 points? Well, that may be an obvious thing, or how many lines are there through 4 generic lines? You look at the space of these geometric objects and so it may not be obvious it's finite dimensional, but the fact that it's a 0-dimensional space is little less non-trivial. I mean, okay, a 0-dimensional space sitting inside a compact space should be finite. So yeah, not obvious, yes, but you would expect it to be finite. So I would maybe rephrase it a little bit. A formula for that in principle can give you an answer for this. Yes, I would agree there. Same with the case of counting nodal curves in P2. So yeah, okay, maybe I'll say it this way. If you manage to figure out how many of these guys are irreducible, that thing is a little bit non-trivial, subtract that off, that should give you the answer I have. And so since we are on that, so this is for G is equal to 0. If one has a formula for this for D and all G's, okay, that in principle gives you a formula there. Okay, so since this is only for G equal to 0, yeah, that is the stronger thing. But if this was a formula for all G and all D, then I mean, both have same amount of information. Yes. And so that is one thing we want to study in the future, do this for higher G. Okay, and so brief word about the method. So the basic idea is essentially not essentially, almost exactly the same as what Kontsevich Manin used. It's the following thing. So let us look at the calculation of LD. Just degree D curves in P2 of genus 0. So the crucial idea here is a gluing theorem, which is the following, that so you look at holomorphic maps from a wedge of 2 spheres. So what does holomorphic mean here? Holomorphic means that it's a restricted to each component, it's a holomorphic map, it's a wedge of spheres, and the point at which they are identified, each of the 2 maps agree. That is the meaning of holomorphic. And degree D means the sum total of the degrees. Okay. So you look at the counts of maps such that, so you have a domain like this with 4 special points on this domain. Let's call them x1, x2, x3 and x4. x1 and x2 are on the upper half, x3 and x4 are on the lower bubble. So x1 hits a line, x2 hits a line, x3 hits 1 point, x4 hits 1 point. Okay, and the image of this map contains the remaining points. So I don't have much time to say this in greater detail. Let me just quickly finish this. So you can, it's not obvious, but again, by a simple dimension counting argument, you can see that this is a finite number. So you are looking at degree D maps. So degree D maps means map which split as D1 and D2 such that D1 plus D2 is D. And it satisfies the constraint that the first half, this D1 part, hits a line, hits another line. I mean, this point hits this line, this point x2 hits this line, this point goes to P2 and x4 goes to P3, and the rest of the points lie in the image. And there is another number which is the same thing, except that my x1 and x2 are on two different halves, and x3 and x4 are on two different halves. And rest of the things lie in the image. And the gluing theorem is that these two numbers are equal. Okay. So it may not look like a very useful statement, but what you have to believe me is you can individually compute each of these numbers. Computing this is very easy. This is very soft combinatorics. And computing the other number, which I have written on that board, that is also very easy. It's very soft combinatorics. And from this, one of them will involve this number of rational degree D curves through 3D minus 1 points. Equating these two things, you get a recursive formula in terms of ND prime. Okay, it's a recursive formula in terms of lower NTs. Okay, which is a full formula. You just need the initial condition, which is n1 is equal to 1. And that gives you n2, n3, n4, everything. Okay, and basically the thing is, what we realized is that the same argument works if we are looking at degree D curves in not just P3, we are looking at planar degree D curves in P3. This basically a similar argument works. You have to intersect it with the right divisors and equate them. The only difficulty is actually calculating these two numbers. Okay. In order to actually get the final formula, you have to actually be able to calculate these two numbers. That is a little bit more involved. Okay. But anyway, we can calculate that, and that does give us, at least algorithmically, we can calculate it, and it does give us a formula. I'm done. No, I mean, this you have to, I mean, basically, you have to use bare bones definition for this. I mean, you have to use the basic definitions of, I mean, you have to start from scratch and calculate some Euler classes for this. You have to make the right setup, set up a bundle and calculate its Euler class.